If you are joined the session, then please write your name and roll number there in the chat box and let me know whether the screen is visible. If you are joined, then let me know whether the screen is visible or not. Am I audible to you clearly? And please reply all of you so that I come to know, so that we will start the session. If you are joined the session, type your name there in the chat box, please, so that we can start the session. All of you. Screen is visible, and if I am audible to you all, then reply there in the chat box so that we can start. Okay, so we'll start now. So I think we should not wait, we should start. So listen here, we have already discussed, and you know that is the formula for machining time calculation. And so it is visible, it is shown there on the screen. That is, this one is the generalized formula for calculating the machining time. So what is that formula? T is nothing but equals to L divided by F into N. So what is T? So that is nothing but the total tool travel length, or we can say that is nothing but the length of tool travel, that is nothing but the L. And whatever this, that is nothing but the L, and whatever this, that is the F and N. So F is nothing but the feed, N is nothing but the RPM, and so that already you know. So whatever this L is there, so basically this L is nothing but equals to the, that is what is just now I have told, that is the length of tool travel. So length of tool travel will be nothing but equals to the total length of the workpiece plus we can say approach length plus we can say over travel. And so that is nothing but the total length of tool travel. So whatever the total length of the workpiece which you want to machine, whatever the approach length, that is before it is touching to the workpiece, so few distance before we are going to keep the cutting tool, and whatever the over travel, so that is nothing but the O, or we can say over travel means though the total length the cutting tool has passed, then few distance it will move there, so that is nothing but the over travel. So whatever the F is there, so that is nothing but the feed in mm per revolution, N is nothing but the RPM, and this is what is, this is nothing but the machining time for one pass. And so accordingly whatever the number of passes are going to be there, so those will be multiplied there. And so this already I think you know, that is the generalized formula for calculating the machining time. Then again you know that how to calculate the cutting speed, that is nothing but the V. So cutting speed is nothing but equals to, we can say pi dn divided by 1000. And so I think this already you know, pi dn divided by 1000. So whatever this D is nothing but the diameter of the workpiece in case of this lathe machine, N is nothing but the RPM, and if this D is in mm, N is in RPM, then you are going to get, by using this particular formula, you are going to get the cutting speed in meter per minutes. Okay, so this already you know there. And so accordingly you can calculate, if the diameter of the workpiece, if it is known, RPM if it is known, you can calculate the cutting speed, or if the diameter of the workpiece if it is known, cutting speed if it is known, then you can calculate the RPM at which that particular workpiece is to be rotated there. And so this already you know. So here you can see the simple numerical on the same, that is the statement of the numerical is, that is find the time required for one complete cut on a piece of work 350 mm long and 50 mm in diameter. The cutting speed is 35 meter per minute and the feed is 0.5 mm per revolution. And so this is the simple numerical. So accordingly you can note down the data which is given, that is length of the workpiece is given, that is 350, 350 mm. Then we can say the diameter of the workpiece is given, that is 50 mm, that is 50 mm. Cutting speed is given, that is 35 meter per minute. Feed is given, that is nothing but equals to 0.5 mm per revolution. Mm per revolution. So here what you have to calculate? That is nothing but you have to calculate, that is the time required for one complete pass. That is nothing but the machining time you have to calculate there. So either you can calculate first, that is the number of revolution required for the complete cut, and accordingly you can calculate the time required for the complete cut. So or you can write directly the generalized formula, that is machining time is nothing but equals to L divided by F into N. So L is known, F is known, but N is not known. So we can calculate the N by using this particular formula. So that is nothing but cutting speed is nothing but equals to pi dn divided by 1000. So here the d is known, N is known. So definitely we can calculate the N. So N is nothing but equals to, we can say the 1000 into 35 divided by this pi into 50. So accordingly we can get the N in RPM, and N we can get in RPM. So if N is known, you know the formula, that is the machining time calculation, formula for machining time calculation, that is nothing but equals to L divided by F into N. So what is L here? L is nothing but the total length of workpiece plus this approach length plus this over travel, and so that is the L. So here basically the approach length is not given, over travel is also not given. So we can consider we may not consider those, that is the approach length and the over travel. So L is nothing but equals to, here we can say that is equals to 350, that is equals to 350 divided by this F, that is equals to 0.5 into N, and N just now we have calculated, that is N is nothing but equals to 22.5 RPM, and so we can get the machining time, so that is nothing but equals to 3.14 minutes, and so very simple. So we can calculate the machining time directly, or step by step we can write like this, that is T is nothing but equals to L divided by F into N, and F into N. So this formula by using this we can calculate the T, and so very simple. So again the numerical may be like this. The next one, that is the statement of the numerical, is a steel shaft of 25 mm diameter is turned at a cutting speed of 50 meter per minute. Find the RPM of the shaft. So very simple. We know the formula for cutting speed, that is V is nothing but equals to pi dn divided by 1000. So accordingly here cutting speed is given, that is nothing but equals to 50 meter per minute. Diameter is given, that is 25 mm, and what you have to calculate, that is you have to calculate N. You have to calculate what you have to calculate, that is N. So very simple. D is known, cutting speed is known, so N you can calculate. Okay. So such kind of numericals is expected that you must know there. Okay. So very simple it is. Any doubt in this? So I think this is clear. So second numerical. So here you can see the statement of the numerical. It may be like this, that is, estimate the actual machining time required for the component C40 steel shown in figure. The available spindle speeds are 70, then 110, 176, 280, 440, 700, 1100, 1760, 2000, 2800. Use a roughing speed of 30 meter per minute and finish speed of 60 meter per minute. The feed for roughing is 0.24 mm per revolution, while that for finishing is 0.10 mm per revolution. The maximum depth of cut is 2 mm. Finish allowance may be taken as 0.75 mm. Blank to be used for machining is 50 mm in diameter, and here the blank, that is what is the component is shown in this particular figure, and again it is mentioned that is take over travel of the tool is equals to 2 mm. So if you go through this particular statement of the numerical, so you can find that too much data is given. So step by step the same thing, you have to note down the data which is given. So when we go through the data which is given here, so you come to know that the spindle speeds which are available there on the lathe machine, so it is mentioned. And so from this you come to know that whatever the RPM which you have calculated, so nearer to that particular RPM you supposed to take the values. Okay. Then again it is mentioned that is the for roughing. Again it is mentioned that is the for roughing the maximum depth of cut, it is mentioned that is 2 mm. That is nothing but the maximum depth of cut which can be taken on this particular lathe machine is equals to 2 mm. So when it is mentioned 2 mm, so you have to understand that first of all you have to calculate that how many number of passes is required to be carried out there. Okay. So required to be carried out there. So just see, first of all you can we will go step by step. So first of all we will calculate stock to be removed, that how much stock you supposed to be removed there. So what is the stock to be removed? So blank size is given, that is equals to 50 mm minus, here in the sketch it is mentioned the diameter, that is 542 mm. So 50 mm minus so 50 mm minus 42 divided by 2, so it is equals to 4 mm. So stock to be removed, so that is the 4 mm stock, the maximum stock you supposed to remove there. Again it is mentioned that is finish allowance is equals to 0.75 mm. So what it indicates, or what is the meaning? Finish allowance is equals to 0.75 means in the finish cut, so this is the maximum depth of cut you can take, that is equals to 0.75 mm. Okay, are you getting this? So here this is the maximum depth of cut which can be taken in the finish cut, and means here you can understand that is the two cuts are going to be there, that is the roughing cut and the finishing cut. So first of all we will calculate the machining time which is required for roughing cut, and so for the roughing, first of all you have to calculate that is the roughing stock which is available there. And so what is the roughing stock? The maximum stock which is available is equals to 4 mm minus finish allowance, that is 0.75 mm. So is nothing but equals to 3.25 mm, means 3.25 mm. So this is the maximum stock which is available or available for removing, or this is the maximum stock, or this is the material which you want to remove there in the roughing cut. And so here you know that is the maximum depth of cut which can be taken. It is mentioned there in the numerical is equals to 2 mm, and the roughing stock which is available is equals to just now we have calculated, so that is nothing but equals to 3.25 mm. Means obviously you can understand that is the 2 roughing passes will be required there. And so in one roughing pass 2 mm material can be removed maximum, and whatever the remaining material is there, so in the another roughing pass, so it can be removed there. And so as usual you can write the formula for the machining time calculation, that is L divided by F into N. So from that you come to know that is length of tool travel is known, feed is known, but N is not known. And N is not known, and for calculating the N, so you can write down the formula, that is N is nothing but equals to, or you can write that is V is nothing but equals to pi dN divided by 1000. So from this particular formula, so you can calculate the N. And so you can calculate the N. So what is N? N is nothing but equals to V multiplied by 1000 divided by pi into D. And so same thing it is written, N is nothing but equals to, that is 1000 multiplied by D, and N is nothing but equals to not multiplied by D, that is multiplied by V, that is 30. So that is 1000 multiplied by V, that is 30, divided by pi into D. So what is D? So basically in the roughing cut, basically in the roughing cut 2 passes are going to be there, 2 roughing passes are going to be there. So definitely whatever this D is going to be there, so that is nothing but the D we are going to take as a average diameter, because 2 roughing passes are going to be there, and that's why we have to take this D is nothing but equals to average diameter. So what is average diameter? That is the blank diameter 50 plus 42. And so here it is, here we can see 50 plus 42 divided by 2. And so that is the average diameter we have to take, because 2 roughing cuts are going to be there. So it is equals to 46. And so here it is mentioned 46. So accordingly you can calculate the N, and it is coming around, that is 207.59. So whether this particular speed is available there on the lathe, on this particular lathe machine which is mentioned there in the numerical, so it is not available. So what you have to do? You have to take the nearer cutting speed. So here you can say the nearest RPM available from the list is equals to 176 RPM. And so nearest from the list is 176 RPM, because if you consider that is 280 RPM, so which is very high compared with this 207 as we have calculated there, so nearest is nothing but equals to 176 RPM. And so here we can get the N is nothing but equals to 176 RPM. Okay. So 176 RPM we have calculated, N we have got there. So we can substitute these values in this particular formula, that is machining time calculation is nothing but equals to L divided by F into N. What is L? L is nothing but equals to, we can say, approach length plus over travel. So basically in the numerical over travel is mentioned. So we can say machining time calculation is nothing but equals to total length of the workpiece plus this over travel divided by this F into N. So what is total length of the workpiece? So that is nothing but equals to 120. What is over travel? That is nothing but equals to 2 mm. It is mentioned. What is F? And so here you have to take f, that is the roughing speed, that is 0.224, and n already we have calculated, that is 176 rpm. So after calculation, you can get the machining time is nothing but equals to this 2.89 minutes. And so this machining time is there for one pass. And so how many roughing passes are going to be there? 2 roughing passes we have calculated. So this multiplied by 2, so that will be the machining time for roughing cut. And so similarly you have to calculate for finishing cut. So as usual, you know the cutting speed formula, that is V is nothing but equals to pi dn divided by 1000. So from that you can calculate the n. So n is nothing but equals to, we can say 1000 multiplied by V divided by this pi into d. So here 1000 multiplied by this V cutting speed, that is 60 it is mentioned for the finishing cut. So divided by this pi into d, we have to calculate, d we have to take. So what is d, which is mentioned there in the sketch, that is equals to 542 mm. So d is given, that is 542 mm. So substitute all these values. So n you can get, that is 439.05 rpm. And so this we will get the n, and so n we will get. So again you have to see whether this particular rpm which you have calculated there in point, or which we are getting there in the point. So this particular cutting speed is not available there, and not available there on the lathe machine which is mentioned. So again what you have to do, the same thing, that is the nearest rpm available from the list you have to take, and the nearest rpm available from the list is nothing but equals to 440 rpm, and 440 rpm. So that is the nearest rpm which is available there, and a nearest rpm which is available there. So again substitute those values in the machining time calculation formula, that is L divided by F into N. L is nothing but equals to 120 plus this over travel, that is 2 mm, then that is the F into N. N we have already just now calculated, that is 440 rpm. So substitute these values, so we can get the machining time. So that is nothing but equals to 2.77 minutes. And so only one finishing cut and 2 roughing cuts are going to be there. So total machining time will be nothing but equals to, the total machining time will be nothing but equals to the machining time for roughing cut, machining time for roughing cut, and the machining time for finishing cut, and the machining time for finishing cut. So machining time for roughing cut, that we have calculated, that is 2.898. So 2.898 multiplied by 2, so 2.898 multiplied by 2, because 2 roughing passes are going to be there, plus this whatever the machining time which we have calculated for finish cut. So that is 2.77, and so this will give you the value, that is the total machining time. And so to do this calculation and calculate the total machining time, so it comes around, that is 4 point something minutes. And so in minutes, so you are going to get the machining time. Yes, it is visible, and have you understood this? Yes, any doubt in this, please? Yes, have you got this? Please reply. Okay, so this is for the lathe machine, we can say. So for the drilling machine, again you can calculate the machining time. The formula is going to remain same. That is the machining time calculation is nothing. Machining time is nothing but equals to T divided by machining time calculation is nothing but equals to L divided by F into N. And so F, that is nothing, that will be there in mm per, that is F will be there in minutes per, that is in mm per revolution. F, that is the cutting speed, and N is in RPM. Okay. So what is L here? That is the total length of tool travel. And if you look towards the lathe machine, if you look towards the drilling machine or the drilling operation, the total length of tool travel, so will be nothing but equals to length of the drill point plus over travel length plus length of workpiece plus this approach length of the drill, and so that total will give you the total length of tool travel. So that is nothing but equals to L1 plus this L2 plus L3 plus this L4. And so whatever these other things, other points are there. So if it is given, then you can consider. If it is not so, then those may not be considered, and you are going to calculate the machining time. So basic formula is going to remain same, that is L divided by this F into N. And so accordingly, this is the simple numerical. You can see that at what speed, the statement is at what speed a 20 mm drill will run for a cutting steel at 25 meter per minute surface speed. And so N, you have to calculate that at what RPM the drill is required to be rotated. And so whatever this D is there here in the cutting speed, so in case of this lathe machine, it is the diameter of the workpiece, but in case of this drilling machine, so it will be the diameter of the drill bit. Okay. And what will be the depth of cut? So in case of this lathe machine, depth of cut will be nothing but equals to, we can say, the distance between the finished surface and the unfinished surfaces, that is D1 minus D2 divided by 2. And in case of this drilling machine, what will be the depth of cut? So depth of cut will be nothing but equals to the diameter of the drill divided by 2, and so that will be the depth of cut. And so this already we have discussed in the regular session. So here, by using the same formula, that is the cutting speed, we can calculate the N. So here this D is known, cutting speed is given, so N can be calculated. Another numerical we can see. So here the statement of the numerical is a hollow workpiece of 60 mm outside diameter and 150 mm length is held on a mandrel between a center and turned all over in 4 passes if the approach length is equals to 20 mm, over travel is equals to 12 mm, average feed is equals to 0.8 mm per revolution, cutting speed is given 30 meter per minute, and you have to calculate the machining time. So simple formula, generalized formula that you have to note down, that that is T is nothing but equals to L divided by F into N. So here this L is known, F is known, but N is not known. So N you can calculate, that is V is nothing but equals to pi dN divided by 1000. And so from that you can calculate the V, and so V can be calculated. So V if it is known, once V we have calculated, so substitute this L, the value of this total tool travel length or length of tool travel, and the cutting and the feed and RPM. So total length of tool travel is nothing but equals to total length of the workpiece plus this approach length plus this over travel. So divided by this F into N. F into N. And so what is F which is given? That is 0.8 mm per revolution. N just now we have calculated, that is 159.15. So you can get the machining time is nothing but equals to 1.43 minutes. So total machining time is nothing but equals to number of passes multiplied by T. So how many number of passes? So it is mentioned there in the numerical, that is the 4 passes are required to turn the workpieces, and so 4 multiplied by the time required for 1 pass, that is 1.43. so 4 multiplied by this 1.43, so we can get the machining time, that is nothing but equals to 5.72 minutes. Okay, so such kind of numericals are there in your syllabus. So whatever the numerical which we have discussed, and that is the whatever the numerical we have discussed. So if you understand all these particular numericals, then up to this much depth the numerical may be asked there in the university examination question paper. And so any doubt in this? And so such kind of numericals can be asked. And so this is the another numerical, that is what is the machining time to turn a diameter given in the figure, and so different diameters which are given in the figure. The material is brass, the cutting speed is mentioned, that is 60 meter per minute. Feed is given, that is 7.5 mm per revolution. The depth of cut is mentioned per pass, that is for 1 pass it is mentioned, that is 3 mm, and so that is the maximum depth of cut which can be taken there. So in the similar way you can solve this numerical, that is you can calculate the you can first of all you can write down the machining time calculation formula, that is T is nothing but equals to L divided by N, that is for 1 pass, and multiplied by the number of passes. So here L is known, F is known, N is not known, so accordingly you can calculate the N by using the formula. That is V is nothing but equals to pi d n divided by 1000. So again it is mentioned, the maximum depth of cut is mentioned there 3 mm. So as usual whatever we have discussed there in the previous numerical, so you have to calculate that how many number of passes will be required there. And so here by using this particular, here it is mentioned that is d minus d divided by this 2 into depth of cut, and so you can get the number of passes which are required. So it is nothing but equals to 3.33. So say that is the 4 passes will be required there, and so accordingly you can calculate the machining time for 1 pass and multiply by the number of passes, and you can get the total machining time, that is T1 plus T2 is nothing but equals to, you can get the total machining time. And so like this particular numerical also can be solved. Okay, so this is I am going to share with you. So another thing what I want to discuss, that is nothing but the to how to calculate the index crank moment. And so basically there are the different indexing method, and by using the different indexing method, so you can calculate the index crank moment, and according to the equal number of divisions which we required. So how many equal number of divisions which we required there, so accordingly one of the indexing method can be selected, maybe the direct or the rapid indexing, maybe plain or the simple indexing, or it may be the compound indexing, then differential indexing, or it may be the angular indexing. And so this already you know that according to the equal number of divisions, that how many equal number of into how many equal number of divisions which you want to divide the peri there. So according to that, the one of the indexing method will be selected there. And so directly we will discuss that how to calculate the index crank moment. So for each method there will be the formula to calculate the index crank moments there. And so if it is the direct and simple indexing, if it is the indexing method, that is nothing but the direct or the rapid indexing, then the formula is nothing but equals to 24 divided by n. And so I am not going to discuss that already we have discussed. That is the formula is nothing but equals to 24 divided by n. And so if you want to divide, and here this PPT is already I have shared. So if you want to divide the surfaces into 6 parts, then we can say 40 divided by n. So accordingly we can calculate the index crank moment, that is 4 holes you have to move the index crank. And so directly I will discuss the numerical. And so this is what is the formula, you know, that is in the simple indexing, that is 40 divided by n. So here we can discuss the numerical directly, that is the indexing required to cut 8 flutes. And so 8 flutes you supposed to cut there, and for that particular purpose you have to calculate the index crank moment. So what is the formula for index crank moment? That is 40 divided by n. And as far as the simple indexing which is concerned, and index crank moment is nothing but equals to 40 divided by n. So what is n? That is the equal number of divisions which we required. So that is the n. And here this n here it is mentioned there in the numerical, that is 8. And so 40 divided by 8, and 40 divided by 8 is nothing but equals to 5. So you can say 5 full turns of the index crank will be required. Okay. So again the another numerical, and so this PPT also I have already shared. The indexing required to cut 7 flutes, and 7 flutes are required to be cut there, or we can say in another word we can say that is we want to divide the peri into 7 equal number of division. That is nothing but the equal number of divisions which we required, that is nothing but the n. Okay. So same formula, that is 40 divided by n, and here the n is nothing but equals to 7, and that is the equal number of divisions, or here it is mentioned there in the numerical, that is the 7 flutes, that is the 7 equal number of divisions which we require. So 40 divided by 7, 40 divided by 7. So this 40 divided by 7 can be written as, that is 5:5 by 7. So how it can be calculated? So do the division. So that is, here you can write 40, here you can write 7. So here you can say, here we can get the division of 5, that is 7 multiplied by 5 is nothing but equals to 35. And so 35. So here you can say we can get this is nothing but equals to 5. Okay. So we can say we can write that is 40 divided by n can be written as 5 is to 5 by 7. So 5 complete turn of the index crank, and then what you have to do, that is 5 holes is to be moved in 7 whole circles, and a 5 hole is to be moved in 7 whole circles lying on the index crank, and so it can be written like this. And so there is an angular indexing, that is you supposed to calculate you supposed to divide the peri into a angular equal number of division, and so for that particular purpose so we know that is total complete turn is nothing but equals to 360 degree. So here you know that is 1 by 40 turns is equals to 9 degree. So for calculating the angular index crank moment, so this is the formula. So from where the 9 has come, that is the 40 teeth are there on the spindle, and we know that is total rotation is nothing but equals to 360 teeth 360 degree. So from that we can get that is 9, and so we can say index crank indexing in degrees, or the index crank moment in degrees is nothing but equals to number of degrees required divided by 9. And so by using the same formula, so we can calculate the index crank. So here the numerical statement is calculate the indexing for 45 degree, and so here we can say indexing or the crank moment, index crank moment is nothing but equals to the same formula, the number of degrees required. So how many degrees which we required to divide, that is the divide into equal number of degrees, that is 45. So 45 divided by 9, so here it is nothing but equals to 5. So that is the 5 complete turns, and so we have to take the cut, then 5 complete turns of the index crank, then another cut, again 5 complete turns, then another cut. So like this. So that is the index crank in degrees. So we can calculate the index crank moment to divide the peri into that many equal number of angular division. Okay. So in the same way, calculate the indexing for 60 degree. So again the formula, that is the same formula here, that is the number of degrees required divided by 9. So here the 60 divided by 9. So again this 60 divided by 9 can be written as same way, that is 6 is to 2 by 3. So here the 6 full turns plus 12 holes we have to move into 18 whole circle, and so basically what is done here, that is numerical as well as the denominator is multiplied by 4, and is multiplied by 4, and not 4. And multiplied by what? And so that those many whole circle must be available, and for that particular purpose the numerical as well as the denominator will be multiplied by certain by same number, so that there will not be the difference in the values as far as the numerator values and the denominator values which is concerned there. And so what you have to do, and so you have to multiply the numerical and denominator by which number here, and so here you can say we can multiply the numerator and the denominator by 6, and so you can get here, that is 6 is to 12 by 18, and 6 is to 12 by 18. So why you have to multiply the why you have to multiply the numerator and denominator, because 3 whole circles line is not available there on the index crank. And so this already we have discussed in detail in the theory, and in the session, in the theory session, theory lectures, in the regular theory lectures. So for that particular purpose, those whole circles must be available there on the index plate, and for that particular purpose here we have multiplied the numerator and the denominator by the some number. Here it is multiplied by 6, and so we can get the we can write this, or we can say 6 is to 2 by 3 can be written as 6 is to 12 by 18, and so that is nothing but the 6 full turns plus this 12 holes you have to move on 12 holes you have to move in 18 hole circles. Okay, so accordingly the angular crank moment can be calculated. Another numerical, that is calculate the indexing for 24 minutes, and here it is mentioned not degree but it is mentioned in minutes, and so we can say degree is multiplied by divided by 9, so that is the formula. And what is the formula I am saying? This is, if you want to divide the peri-peri into in degrees, then it will be multiplied by 9, that is divided by 9. So if you want to divide the peri-peri into minutes, then it will be nothing but equals to 9 multiplied by, then it will be nothing but equals to, degrees can be converted into minutes, that is 9 multiplied by 60, and again if you want to divide it into second, then again 9 multiplied by 60 multiplied by again 60, and so here it is 9 multiplied by 60, that is 540. Okay, because it is given in minutes. So 24 divided by 540, so that is nothing but equals to 4 divided by 9, and so 4 divided by 9, so again we can say it is nothing but equals to 1 divided by 22.5. So again we can say this 22.5, so that particular whole circle is not available there, so nearest whole circle can be taken, that is 24 holes. So we can say one holes we have to move into 24 whole circles, and so basically this 24 whole circles which are available there on the index crank. And so again this numerical is also there in the PPT, that is 24 degree 30 minutes. So what you have to do here, whatever this 24 degree is there, so that can be converted into minutes. So 24 multiplied by 60, so it is equals to 1440 minutes, and you have to add this, that is 30 degree which is mentioned there in the numerical, so it is equals to 1470 minutes. Okay, then we know the formula, that is when it is in second, then you have to divide it by 540, when it is in degree, then you have to divide it by 9. So here it is, we have converted all this into second, so not in second, that is in minutes. So 1470 minutes you are divided by this 540, so we can get, that is 2 is to 13 by 18, so that is the 2 full turns and 13 holes you have to move in 18 whole circles. And so rapidly we have discussed all these numerical, that is the numericals on machining time calculation for lathe machine and machining time calculation for drilling machine, and also the how to calculate the index crank moment. So this is all from my side. So if you are having any doubt, please ask. Please type in the chat box so that we can discuss. Otherwise, we will stop here. So again I think today will stop here then. Again, if you are having any doubts, you can meet me in the college and get your doubts clarified. So thank you all of you. Thank you for joining. So we will stop here.